The divide and conquer method is a fundamental approach for creating efficient algorithms. It involves breaking a larger problem into smaller subproblems, solving these recursively, and combining their solutions to address the original issue. A classic example is merge sort, where the array is divided, sorted in smaller chunks, and merged back. In this chapter, we focus on the applications of divide and conquer and the mathematical tools needed to analyze the recurrences that arise from this method. Recurrences are equations that represent the running time of recursive algorithms and are pivotal for understanding their efficiency. By the end of this chapter, you'll gain the tools to both apply and analyze divide and conquer strategies effectively. This approach has 3 key steps: divide the problem into smaller subproblems, conquer these recursively until reaching a base case, and combine the results. The base case is directly solvable without further division, ensuring that recursion bottoms out. This strategy is not only versatile but also lays the foundation for analyzing algorithm complexity through mathematical recurrences, which describe the function's value based on smaller inputs. Divide and conquer algorithms share 3 defining characteristics: divide, conquer, and combine. First, the problem is divided into smaller instances, such as subarrays in sorting or submatrices in matrix multiplication. Second, these subproblems are solved recursively, leveraging the structure of the problem. Finally, the solutions are combined into a single output, reflecting the solution to the original problem. Recursion continues until a base case is reached, where the problem size is small enough for direct computation. By recursively solving and combining, the efficiency of divide and conquer algorithms often surpasses straightforward iterative approaches. For instance, in merge sort, dividing the array allows operations on smaller, sorted portions, culminating in an efficient merge step. This process demonstrates the power of recursive problem solving and highlights the importance of analyzing how subproblems interact and scale. To understand divide and conquer algorithms, analyzing their recurrences is essential. A recurrence describes the behavior of a function based on smaller inputs. For example, the recurrence t of n equals 2 times t of n over 2, plus theta of n represents the merge sort algorithm's running time. Recurrences combine recursive cases, where smaller instances are called, and base cases, where direct computation occurs. In general, recurrences have 2 components: recursive calls, representing problem decomposition, and base cases, defining direct solutions. The mathematical analysis of these recurrences enables us to estimate algorithm efficiency. For divide and conquer algorithms, understanding recurrences is the key to predicting their performance and optimizing their design. Algorithmic recurrences describe the running times of divide and conquer algorithms. These recurrences adhere to 2 key properties. For small inputs, t of n equals theta of 1, representing constant time for base cases, and for larger inputs, every recursion path terminates in a finite base case. For example, the recurrence t of n equals 8 times t of n over 2, plus theta of 1 for matrix multiplication ensures that recursion stops as problem size diminishes. The running time depends on recursive calls and the base case efficiency. Recurrences help in understanding how the algorithm scales with input size, which is critical for verifying correctness and optimizing performance. For well-defined recurrences, the mathematical solutions predict the behavior for any input size. For analyzing divide and conquer algorithms, conventions simplify recurrence representation. If no explicit base case is given, the recurrence is assumed to terminate with a base case t of n equals theta of 1. This flexibility allows analyzing running times without concern for small input details, focusing instead on scaling behavior. Dropping floor or ceiling functions simplifies expressions without altering asymptotic results. For example, t of n equals 2 times t of n over 2, plus theta of n approximates merge sort's performance, revealing t of n equals theta of n log n. Similarly, for irregular problems, inequalities may be used, such as t of n is less than or equal to 2 times t of n over 2, plus theta of n, analyzed through big O notation for upper bounds. Such conventions ensure clarity and applicability across diverse problems. Divide and conquer and recurrences are intertwined, particularly in analyzing the efficiency of algorithms. This chapter explores matrix multiplication as a key example. The simple divide and conquer algorithm divides an n by n matrix into 4 smaller n over 2 by n over 2 submatrices. Using recursion, it computes the matrix product, characterized by the recurrence t of n equals 8 times t of n over 2, plus theta of 1. The solution to this recurrence is t of n equals theta of n cubed, which matches the running time of the traditional triply nested loop method. However, this straightforward divide and conquer approach can be optimized. In the next section, we examine Strawson's algorithm, an asymptotically faster alternative. The ability to analyze such algorithms using recurrences reveals their strengths and weaknesses, highlighting the role of efficient recursion in reducing computational complexity. Strawson's algorithm revolutionized matrix multiplication by reducing the number of subproblem multiplications from 8 to 7. It uses the recurrence t of n equals 7 times t of n over 2, plus theta of n squared. The solution to this recurrence is t of n equals theta of n to the power of log base 2 of 7, which approximates theta of n to the 2.81. This improvement demonstrates the power of divide and conquer, as reducing recursive work can have a profound impact on algorithm performance. The key innovation in Strawson's algorithm is balancing increased work in the divide and combine steps with fewer recursive multiplications. This trade-off results in a less bushy recursion tree, ultimately achieving better asymptotic performance. Strawson's approach underscores the importance of mathematical analysis in discovering more efficient algorithms. The regular divide and conquer algorithms, unlike the regular ones, often divide problems into subproblems of unequal sizes. For example, consider a problem where the recurrence is t of n equals t of n over 3, plus t of 2n over 3, plus theta of n. Here, the subproblems are of size n over 3 and 2n over 3, respectively. This recurrence has the solution t of n equals theta of n log n, showcasing that irregular recursions can still lead to efficient algorithms. Irregular recurrences reflect real-world scenarios where problems cannot always be divided evenly. Analyzing such cases requires understanding how the uneven distribution of work affects performance. These recurrences provide a mathematical framework for predicting and improving algorithm efficiency in practical applications. Solving recurrences is central to analyzing divide and conquer algorithms. This chapter introduces 4 methods: substitution, recursion tree, master method, and acrobacy. The substitution method involves guessing the solution and proving it using induction. The recursion tree method visualizes the recurrence as a tree, summing costs at each level. The master method provides a cookbook approach for solving recurrences of the form t of n equals a times t of n over b, plus f of n, where a and b are constants. Lastly, the acrobacy method extends these techniques to handle more complex recurrences. Each method serves different needs. While the substitution method is versatile, the master method offers simplicity for standard recurrences. The acrobacy method, though more general, requires calculus. Understanding these tools equips you to analyze both common and irregular divide and conquer algorithms effectively. The substitution method is a powerful yet straightforward way to solve recurrences. It has 2 steps. First, guess the form of the solution using symbolic constants, and second, prove the solution correct using mathematical induction. For example, to solve the recurrence t of n equals 2 times t of n over 2, plus theta of n, you might guess t of n equals theta of n log n. Substituting this guess into the recurrence and proving it with induction confirms its validity. This method works well for proving both upper and lower bounds. However, generating an accurate guess can sometimes be challenging. Tools like recursion trees can provide intuition for making better guesses. Ultimately, mastering the substitution method enhances your ability to analyze and understand recursive algorithms with precision. The recursion tree method provides a visual approach to solving recurrences. In this method, each node represents the cost of solving a subproblem, while the edges represent the recursive calls. For example, consider the recurrence t of n equals 2 times t of n over 2, plus theta of n. The recursion tree begins with the root, representing the cost theta of n at the top level. Each child node represents the cost at the next recursive level, which becomes smaller with each division. By summing the costs at each level and then adding these totals, we calculate the overall cost. This method is particularly useful for building intuition about a recurrence's behavior. It also helps guide guesses for solutions, which can later be verified using the substitution method. Although straightforward, it can become complex for irregular recurrences, requiring creativity in determining the total cost. The master method is a practical cookbook solution for solving recurrences of the form t of n equals a times t of n over b, plus f of n, where a and b are constants, and f of n is the driving function. The method involves 3 cases based on the growth rate of f of n compared to n to the power of log base b of a. In case 1, if f of n grows slower than n to the power of log base b of a, the solution is t of n equals theta of n to the power of log base b of a. In case 2, if f of n grows at the same rate, the solution is t of n equals theta of n to the power of log base b of a times log to the power of k plus 1 of n. Finally, in case 3, if f of n grows faster and satisfies the regularity condition, the solution is t of n equals theta of f of n. The master method simplifies solving many standard recurrences encountered in divide and conquer algorithms. The acrobacy method is a more general approach for solving divide and conquer recurrences. It applies to recurrences of the form t of n equals f of n plus the sum from I equals 1 to k of a sub I times t of n over b sub I, where k is the number of subproblems, and the coefficients of sub I and b sub I are constants. The first step is finding the unique value of p that satisfies the equation the sum from I equals 1 to k of a sub I times b sub I to the power of negative p equals 1. Once p is determined, the solution to the recurrence is t of n equals theta of n to the power of p times the quantity 1 plus the integral from 1 to n of f of x divided by x to the power of p plus 1 dx. While the Acrobazzi method is more versatile, it requires calculus and is best suited for recurrences that fall outside the scope of the master method. The polynomial growth condition is an important requirement in the Acrobazzi method, allowing us to ignore floor and ceiling functions in recurrences. A function f of n satisfies the polynomial growth condition if there exists a constant c such that, for every value psi between 1 and phi, the inequality f of n divided by d is less than or equal to f of psi times n, and f of psi times n is less than or equal to d times f of n holds for sufficiently large n. Functions like theta of n to the power of alpha times log to the power of beta of n times log to the power of gamma of n meet this condition. This ensures that the Acrobazzi method remains valid for a wide range of recurrences, simplifying the analysis without altering the asymptotic results. Comparing the master method and the Acrobazzi method highlights their respective strengths. The master method is simpler and ideal for recurrences with equal size subproblems, but it is limited to specific forms. For instance, it works for t of n equals a times t of n over b, plus f of n but cannot handle irregular subproblem sizes. On the other hand, the Acrobazzi method is more general, accommodating recurrences with unequal subproblem sizes and more complex structures. However, the Acrobazzi method requires calculus and checking the polynomial growth condition, which can make it more demanding. When the master method applies, it is usually the preferred choice for its simplicity. Together, these methods form a robust toolkit for solving a wide range of algorithmic recurrences. Understanding the Acrobazzi method and other techniques for solving recurrences is essential for analyzing the runtime complexity of divide and conquer algorithms. These methods enable us to derive asymptotic bounds, such as theta, O, or omega, for various recurrences, providing insights into algorithm efficiency. Mastering these techniques is crucial for designing and optimizing algorithms in both theoretical and practical contexts. From simple methods like substitution and recursion trees to advanced approaches like the Acrobazzi method, each tool serves a specific purpose. By applying the right method for the problem at hand, we can effectively analyze and improve algorithms, ensuring that they meet the demands of real-world applications.